In this lecture, we'll be reviewing how electric charges exert forces on other charges. So these are forces that can act at a distance. The charges don't need to be in contact with each other. And I'll be reminding you of Coulomb's law. Then we're going to be looking at the mechanism by which the charges feel the other charges near them. And that's called an electric field. So a charge will set up an electric field and another charge will sense that electric field. We'll have a look at the field from one point charge, a few charges, and even from a continuous charge spread. And then we'll have a look at the force that a charge experiences from that field. In the next lecture, we'll be having a look at the electrical energy that's associated with these charges or the fields they set up. Experimental evidence convinces us that there are just two kinds of charge, and for no particular reason we've decided to call them positive and negative. So it follows as well that there are two types of forces. There's a repulsive force and an attractive force. Compare this to mass and the forces that you experience between that mass, which are called gravitational forces. There is only one type of mass, which is positive, and there is only one type of gravitational force, which is attractive. Now, the force that between a pair of charged particles is along the line that joins them. So, although these look like complicated diagrams down the bottom, they are in fact just the combination of two free body diagrams. Let's have a look at the free body diagram just for Q1 from the left-hand diagram. First of all, I'm going to draw the line that goes between it and Q2. So if this is a free body diagram for Q1, then we're only interested in the forces that act on Q1. And so we have here the force from charge 2 on charge 1. If you do a free body diagram for Q2, then you'll see the other force that's written in the diagram just to the right. So in fact, this diagram here is actually two free body diagrams rolled into one. Notice that I've given subscripts on these forces. And the reason I've done that is because I'm essentially giving these two forces different names. Why? Because they're different forces. Yes, we know they are the same in magnitude. If you've studied electrostatics before, you'd know that. But the important thing is that they're acting on different charges. They're acting in different directions. So if they're different forces, let's call them different names. That means we're less likely to get confused. Now, it was Coulomb who just started to quantify the forces that there are between charges. One important thing he showed is that the force is proportional to, or inversely proportional to, the square of the distance between the point charges. So here's charge 1, here's charge 2. That distance, that displacement there has the magnitude of r, and the force between them is inversely proportional to r squared. The other thing he showed is that the force is proportional to the product of the charges. Okay, so we've now got from Coulomb a simple physical model that describes the force between 2 point charges. So from that, we can express it as a mathematical model. And that gives us the magnitude of the electric force, both the force of charge 1 on charge 2 and the force of charge 2 on charge 1, is going to be product of those charges, and we're not going to worry about if they're positive or negative because we're going to take the absolute value. The distance between them squared, and our constant of proportionality in air or vacuum is going to be 9 by 10 to the power of 9 newtons meter squared per coulomb squared. Now, K can also be written as 1 over 4 pi epsilon naught. And epsilon naught is known as the vacuum permittivity. It's a very important physical constant of our universe. So we've got a lovely expression that gives us the magnitude of the force between point charged particles. What if we want to find more than the magnitude? What if we want to find the actual vector? So we want direction as well. Well, as we saw before in the diagram of the two charges, there are two forces. So we're going to have to specify, first of all, which force we want to talk about. Let's say we've got, there's charge 1, and we have here charge 2. So this is a free body diagram of charge 2. The forces on charge 2, we know, are going to look like this. So that's the force we're trying to find. Let's call this force the force due to charge 1 on charge 2. Or we can call it F12 for short. Doesn't matter what you call it, just make sure you give it a name and know exactly what you're referring to. Okay, so what we want to end up with is a force where we already know the magnitude and we want the direction to be pointing to the right. Okay, so the vector F12 is going to be, we know the magnitude, K, Q1, Q2, all over R squared. So R is going to be the position of 2 compared to 1. So what that is, it's the R defined here is the displacement vector between 2 and 1. So imagine you started at position 1 and you ended up at position 2. What's your displacement? That's your displacement, R12. Okay, so let's put that one in there, R12. Because if we were to consider charge 1, what's the force on that due to charge 2? Well, we know that our displacement would be a vector that's actually pointing in the opposite direction. Right, so the thing is though, this factor down here is the magnitude squared, right? If you square a vector, you just end up with a magnitude. You don't have a direction anymore. How do we get a direction for this force vector? Well, we know that the force vector must be parallel to our displacement vector. That's good. So we need to multiply this by our displacement vector, R12. But then that gives us the right direction. But now we've mucked around with the magnitude, haven't we? We've multiplied it by the length of this R vector. So we will divide by the magnitude like that. Okay, I'll draw it over on the right hand side. If we have a vector like this, it has a certain length and a certain direction, and we want to have another vector that points in the same direction but only has a length of 1, what we do is we take our original vector and divide it by its length. Okay, so this is equal to the original vector divided by its length. Another way of writing this is r hat. So what we have done here, this is called the unit. This is called a unit vector, isn't it? So it's pointing in the direction of the r vector, but its length is 1. So we could also write this as k q1 q2 r12 all squared times r hat. I've not taken the absolute value of this of these charges here. So that's because if they're both positive, it's going to point in the same direction as r hat. If one of them is negative, then you'll have a negative sign there and it will point in the opposite direction. So it's all good. So, oops, I accidentally deleted that and I thought I was highlighting it. F12. So we have here a full vector expression for the electric force. Okay, so let's apply what we know. This is a one-dimensional system, so we don't have to worry about vectors. Okay, we're going to find the electric force on charge 3. So that means let's do a free body diagram of charge 3. Okay, so we have a positive charge, Q1, to the left. So that means we're going to have a repulsive force. So this force will be force F13. We also have a negative charge on the right-hand side, Q2. So that's going to put an attractive force on Q3. So we're going to have here force on 3 due to charge 2. So you can see we had to consider these two charge pairs. One was charge 1 and charge 3, and the other was charge 2 and charge 3 to find these two forces. And you know what we do when we have a free body diagram? we make a vector sum of the forces. In this case, we don't need to worry about the vectors, do we? It's all in one dimension. So we have going to be F13 plus F23. So let's calculate what those forces are. F13 is going to be K Q1, Q3. We'll just work with magnitudes. This will be R squared. Okay, and this is 1.125 by 10 to the minus 4 newtons. We have F23. This will be K Q2, Q3 over R squared, and that will be 6.75 by 10 to the minus 5 newtons. So the electric force on Q3 is going to be the sum of those forces, which is 1.8 by 10 to the minus 4 newtons to the right. Okay, so now we're working in 2 dimensions. So directions are important as well as just distances. We're going to find again the electric force on Q3. So here's Q3. It's going to feel a force due to Q1, which is going to be along that line that joins them. And it's an attractive force, so it will look like that. Now Q2 will also put a force on it. It'll act along that line. Again, it will be attracted to charge 2. So let's label those forces. This is F13 and this is F23, and those are vectors. So our job is to add F13 to F23 and find out what is that resultant vector. So it looks like the x components are going to vanish. We're just left with a y component, a downward pointing electric force on Q3. So if you want to use the vector form of Coulomb's law, we've got to draw in our position vector. This will be R13. And this one here will be R23. Now you can either write that down mathematically as in terms of the x and y unit vectors. So you could write R13 is equal to, well, this is clearly a 3, 1, 2, 3. This is a 3, 4, 5 triangle, right? So this is pointing 3 in the x direction and it's pointing 4 in the y direction. So you could write it like that. Or you could write it as in terms of its length and angle. So the magnitude of R13, this is going to be magnitude, that'll be 5 centimeters. And the angle is going to be, let's see, arctan of whatever 3 divided by 4 is from the y-axis. Okay, so you might prefer to work in terms of magnitudes and angles or in terms of x and y components. Whichever way you do it, you should end up with the same answer. But when we were studying mechanics, like in projectile motion, we saw splitting things into right angle components was really nice. And so that's the way I'll show you how to solve this. So the one last thing we need to do with the position vector is work out the unit vector in that direction. Okay, so that's going to be this position vector divided by the magnitude, right? So that's 3x hat plus 4y hat divided by the magnitude, which is 5. And I'll just draw that over here so you can see what it looks like. That is r hat there. Points in the direction, the right direction, but it only has a length of 1. Now you can go through the same process and you will find that R23, this is going to be minus 3x hat plus 4y hat, and the unit vector R23 is going to be minus 3x over 5 plus 4y hat. Oh, forgot to put the hat on the x, over 5. So our force on 3 is K Q1 Q3 all over R13 squared times 3 on 5x hat in the x direction and 4 on 5y hat in the y direction. And F23 K Q2 Q3 all over R23 squared times minus 3x hat on 5 and 4y hat on 5. Now, it's quite nice in this example here that the values of Q1 and Q2 and their distances to Q3 are all exactly the same. So summing these two forces turns out to be quite simple. What you'll see, as you expect, I guess, is that the plus 3 on 5 x hat, so the plus the x component from one force cancels out with the x component of the other force. They're pointing in opposite directions. And our net force is equal to it's going to be, let me see, so Q3 is always negative, so we're going to have 9 by 10 to the power of 9 by minus 4 by 10 to the minus 6 by 2 by 10 to the power of minus 6 over 5 squared, or centimetres, 0.05 squared, and we know that in this case it's going to be 2 times 4 on 5 y hat. So what we get is minus 46 newtons. Okay, so minus 46 y hat newtons. In other words, 46 newtons in the negative y direction. So we've got a two-dimensional system here. We've got 3 charges, Q3, Q1, Q2. And you're going to find the force on Q1. So I'll give you a partially worked solution, and I hope that you'll take the time just to prove to yourself that you can remember these basic electrostatic calculations by trying to solve it. So I recommend, first of all, sketch it like we've got it there. Now do a free body diagram of Q1 and imagine what those forces are going to be. So this Q1 is negative, Q3 is negative, and Q2 is positive. So what we expect is that Q1 is going to have a repulsive force in this direction, and it's going to have an attractive force in this direction. So we expect then that that our resultant force is going to look something like this. Okay, so that's what we hope our answer is going to look like, a force vector that's pointing in this fourth quadrant. So in this case, again, I recommend you split into X and Y components. So you would look at, you would find the X and Y components of the forces, and then after that, then you add them. Now the force due to charge 2 on charge 1 is only going to have an X component. So that'll be easy, but the force due to charge 3 on charge 1 is going to have X and Y components. So you'll have to split those up. Then you can add the X components and add the Y component. You can keep them in separate equations, or you can put them in the same equation and just give them an X hat and a Y hat next to them. And then let's see if you get the correct answer. Well, hopefully you will get the force due to chew on charge 1 in the X direction is going to be 1.2 newtons. The force due to charge 3 on charge 1 in the X direction is going to be 0.9 newtons. And the force due to charge 3 on charge 1 in the Y direction is going to be minus 1.6 newtons. So you add these up and we find that the net force is going to have a magnitude of 2.1 newtons in the X direction. Now we're going to spend some time considering how it is that, when you put like charge Q1 there, how does it know that there are other charges there? How does it feel that force? Now, the mechanism in physics that we talk about is a modification to space. So a charge modifies the space around it. And that modification of space is called an electric field. So let's say we put here charge Q1 at a particular position. Then it modifies all the space around it. And so you can imagine if I bring in another charge like Q2 and I put it over here, or over here, or indeed over here, it's going to sense the change in space made by Q1, and it's going to respond accordingly. So you could correctly imagine that the modification of space is like the wells that are used to demonstrate how gravitational fields modify space. But with gravity, remember we only have attractive forces, so we only talk about gravitational wells. Whereas with electric fields and electric forces, we have two types of forces, attractive and repulsive. So you can imagine we don't only have wells, sometimes we have mountains as well. So what actually is an electric field? Is it like a field of wheat? Well, sort of. You can see that the field of wheat in that painting on the right-hand side by Van Gogh. He's demonstrating that everywhere in that field there is a displacement due to the wind velocity. But that wind velocity is not the same at every position in the field. It's slightly different here and there. And in physics, we have a field is as describing something that a quantity that actually has a value at every position in space. Now, we didn't need to think about this before when we were just talking about our mechanics objects that had to touch each other before they exerted forces. But now that we're talking about charged objects, they actually modify all of space around. So let's consider water in a swimming pool. Now, at every position in this swimming pool, water has a temperature. And the temperature also depends on the position in the pool. For example, in the position that describes the bottom of the pool, you might have a very low temperature. In the position, I don't know, in the vicinity of the baby, you might have a very high temperature. But what we have is a temperature which has a value everywhere, and the way it varies with position, and in fact time, is field. It's just going to be a scalar field because temperature is a scalar. Okay, so what about velocity? Water everywhere is going to have a velocity too. Down the bottom of the pool, the velocity might be zero. There might be no current there. In the vicinity of someone diving into the water, there's a lot of splashing going on, so there's quite large currents. So water everywhere has a velocity, and the way that that velocity varies with position, and in fact also with time, is a field. And at this time, it's called a vector field. And that's because the velocity is a vector. Not only does it have magnitude, it has direction. So a field is always going to tell you what is the temperature or the velocity or whatever else at a time and place that you specify. So you specify X, Y, Z, and if it's moving, you have to specify time as well. And that will tell you what is the temperature or velocity at that point. Okay, so here are our charges. We've got a negative charge on the left and a positive charge on the right. And often we only draw things in two-dimensional situations. It's just because it's easier to visualize, easier to draw. Right, so what we know is that our positive charge here is going to modify space around it. And our negative charge is also going to modify the space around it. And so that modification is called the electric field. So we will write electric field is a function of x, y, z, or maybe just x and y. We're not going to worry about time because we're dealing with electrostatics. So electrostatics doesn't change with time. Okay, so what this function is going to tell you is how a test charge is going to react at every position. Okay, so we're going to use this to tell us if I put a test charge here, what's going to happen to it? If I put a test charge here, what's going to happen to it? That's what the electric field is going to help us find out. So that means that we have two important questions that we try to do when we're modeling these situations. One is, given a distribution of charges, 2, 3, thousands of charges, what's the electric field? And then the next common question is, if you have been given a certain electric field, what is going to be the force on a charged particle? Okay, so here is our definition of electric field. It is going to be equal to the force that a test charge feels in an electric field divided by the size of that test charge itself. So say I've got an electric field going on the left-hand side of this screen, and I put my little test charge there, Q0. And then I measure that it experiences a force like that. What that tells me is that at that point there is an electric field that's supposed to be parallel, which is parallel to the force on the test charge. So the direction is the same as the force on the test charge, and the magnitude is equal to the force divided by the test charge. So the units of electric field are going to be units of force divided by, which are newtons, divided by the units of charge, which are coulombs. Okay, so an electric field is always equal to the force on a test charge divided by the size of that test charge. If we rearrange that equation, then we have the force on a test charge is equal to the electric field times the charge itself. This is a very useful equation. So before, we had to know where every charge was located and apply Coulomb's law to every pair of charges to work out what the force of Q was. Now, if someone gives you the electric field, X and Y, for example, then you don't have to worry about where all those other charges are. You simply can work out the force on your test charge just by multiplying it by Q0, and that will give you the force. Simple. You can also see that the sign of the charge is important. So if Q is positive, then we're going to have, let's rewrite it like this. Electric field is F naught over Q naught. So if this is positive, then the electric field is in the same direction as the force. But if Q positive, if Q is negative, then we have a negative sign down here, then the electric field is in the opposite direction of that force. Now, it's all very well, though, to talk about, you know, if you've got the electric field, you can work out what the force on a charge is. What if, you know, you don't know what the electric field is? What if you've actually got to figure it out? Well, what we're going to do now is we're going to find out what's the electric field around a point charge. So we know that the force around a point on a test charge, near a point charge, so let's say this is our source point charge, and this is our test charge. So the force on the test charge is going to be 1 over 4 pi epsilon naught by the product of the source and test charges divided by r squared. Okay, so we know that the electric field around our source charge is going to be the force on the test charge divided by the charge. So that's going to be, the electric field is going to be proportional to the size of the source charge, Q, and it's going to be inversely proportional to the distance from the source charge squared. All right, and so this is a good thing. All right, I said that the field has to have values at every point. Well, you can see that we can vary R to be anything. All right, so electric field does in fact depend on position. So I can make R be equal to 0, 1, 1,000. I can use this equation to find the electric field anywhere. All right, so this is a true field expression. And this is the vector equation. You can see that we use the actual value, not the absolute value of the source charge. And we also have to use the position vector, okay, which is from source charge to position of interest, so the position at which we want to figure out what the electric field is. So let's work through an example. Find the size of the electric field 2 meters from a point charge of 3 microcoulombs. So here's my source charge. It is 3 microcoulombs. And I want to find the electric field 2 meters away. So it could be 2 meters here, 2 meters there, 2 meters. In fact, I'm sure you realize that what we're going to be doing is working out the electric field anywhere on the circumference of a circle that has a radius of 2 meters. So this is the electric field is going to be 1 over 4 pi epsilon naught. Q is 3 microcoulombs. R is 2 meters, so that's 2 squared times R. And what we get is 6,750 R hat newtons per coulomb. The R hat means that the direction of the electric field is going to be in the direction of R to that point. So R to this point over on the top left looks like that. So R hat must be pointing in that direction. So that's the direction of the electric field. So everywhere you go around this circle, the electric field is going to point outwards along the direction of that R vector. The electric field from this is our position. So we've got this is our X and Y, and we want to find it due to this is our source charge that's causing the electric field, and this is the location. So here's our sketch. We always start off with a sketch. There's the origin. So there's my -5 microcoulombs, X and Y. So I want to find the electric field at a position 1.5 to the right, -2 downwards. So that's my point of interest there. Find the electric field at that point. Well, first of all, we've got to find the position vector, right? So the position vector is going to be 1.5, the x component is 1.5, and the y component is -2. Magnitude, well, magnitude squared, we use Pythagoras theorem. That's going to be 5 squared plus 2 squared. So that gives us a magnitude of 2.5 meters, I think. So that means our unit vector is 1.5 divided by 2.5 in the x direction, and the y component is -2. Oh, whoops, I did two minus signs. 2 over 2.5 in, there's the y direction. Okay, so now let's find out the electric field. It's going to be K times the source charge, -5 microcoulombs, divided by R squared, which is 2.5 squared, times R hat. So this will be times 1.5 on 2.5 for the x component, and it'll be -2 over 2.5 for the y. So that means that our electric field is going to be -4,320 in the x direction and plus 5,760 in the y direction, newtons per coulomb. Let's sketch that on so we can see it's going to be, it has a negative x component and a positive y component. So there's our resultant electric field. So the electric field at that point is pointing back towards the source charge. Now we know using free body diagrams already that we can just add forces like vectors. So it turns out that really quite usefully, you can also add electric fields like vectors too. Okay, now this has got a fancy name called the principle of superposition, but essentially what we say is that electric fields, like forces, can be added as vectors. You don't have to multiply them or do anything. So you know that electric field has to have a value everywhere in space, because you can move your test charge around anywhere and it will always feel a force. So it's good to have a way of visualizing it. So how do you visualize something that is everywhere, but it has a different strength and different direction everywhere? So one way to go is in the bottom left. We don't have the electric field everywhere, but we've at least visualized the electric field everywhere on a set of grid points. And you can see that on each of those grid points, there's a little flag, and it points in a direction that is parallel to the electric field at that point. And the magnitude of the electric field, well, instead of being encoded as the length of the arrow, it's encoded as the color of the arrow. Now, another way to visualize electric field is on the right-hand side, and these are electric field lines. There's a website down the bottom of this slide that you can go to, and you can play around putting charges into various positions and looking at the electric fields and visualizing them in different ways. But the important thing about the electric field line distribution diagram is that it shows you the strength of the electric field by how close the lines are together. And it also gives you an idea of the direction of the electric field. So each of these lines starts on a positive charge and goes to a negative charge. And the electric field always points away from the positive and towards the negative. Let's have a look at some more detailed examples. Okay, so let's have a look at a few examples, and I'll show you how to interpret the electric field line images. First of all, we have a positive charge, and you can see that the field lines start from the positive charge and the arrows are directed away from it. Another thing you can see here is how the density of lines reflects the strength of the electric field. So what we can do is we can draw a line, because we're looking at two-dimensional situation. So draw a line. It can be a curved line, and it needs to be perpendicular to the field lines. So the magnitude of the electric field, also called the electric field strength, is proportional to the number of field lines that intersect with the line that you drew. So let's say I'm interested in close to the positive charge, so I'm going to draw a curved line. You can see it's right angles to that field line, and it's right angles to that field line, and it's at right angles to that field line. Now I'm going to draw a line the same length further away. So let's draw one here. So this is about the same length like that. So you can see where I have drawn, where I've centered this, my first red line, there are 3 electric field lines intersecting it. Whereas where I drew my second red line, there's only 1 field line. And that indicates that the field has dropped by about a factor of 3. Let's have a look at some more examples. Here's a dipole, which means we have a point positive and a point negative charge. You can see when it comes to the negative charge, all the field lines end on it. So all the arrows point towards the negative line, the negative charge, and they end there. Some of the field lines are curved, and we can use those to find the direction of the electric field anywhere as long as it's on an electric field line. So let's say we were interested in the direction of the electric field at that point there. What we do is we draw a tangent to that electric field line at that point, and that gives us the direction of the electric field at that point. Let's have another look at a pair of negative charges. Again, you can draw a tangent to the line at some point. For example, here we might be interested, what's the electric field direction at that point? And we'll just draw a tangent like that, and that gives us the direction of the electric field. And of course, you can also do the same trick of drawing a line of a certain length like that, and then comparing it to a line of a similar length, such as this line here, and you can see that there are no field lines going through the line that I've drawn here, so the electric field must be very low indeed. Let's finish off with a continuous distribution. So this is a continuous distribution of charge. Right, so in this instance, you can see if I'm interested in finding the direction of the electric field here at point A, or at point B, or at point C, then the electric field points the same direction. If I draw a line at right angles, like that through A, or like that through B, or like that through C, so all of my lines are, all of my lines are the same length, you can see that 3 electric field lines go through the red line that I've drawn. So the electric field magnitude is the same as well. So what these parallel field lines indicate is that the electric field has a constant direction and magnitude in this particular arrangement. Okay, so where you have a continuous distribution of a lot of positive charges and a parallel distribution of a lot of negative charges, what you'll find is that you have an electric field between there that is constant. It's got always the same direction and always the same magnitude.